Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. One thing, later in this video, you'll hear us mention VHDs, virtual hard disks, which are files that hold a virtual machine's operating system and data, and SAS tokens, shared access signatures that let you securely access Azure storage without a full account key. Now, let's jump in, turning IT knowledge into career opportunities. Last time, you learned how Azure managed disks store a virtual machine's operating system and data. Now imagine that you finally build the perfect server. The operating system is patched, required applications are installed, security agents are running, monitoring is configured, and every setting has been tested. Then your boss says, "Great. We need this exact configuration in West Europe, Southeast Asia, and 3 more Azure regions." Without an image management platform, you might begin copying VHD files, generating SAS tokens, rebuilding configurations, and manually tracking which regional copy represents the approved release. Azure VM Image Builder and Azure Compute Gallery automate and standardize much of that work. Image Builder creates the image through a repeatable process. Compute Gallery organizes it into definitions and versions, replicates approved versions to selected regions, and makes those images available to authorized deployment teams. You still need testing, security validation, lifecycle management, and rollback planning, but you no longer need to rebuild the same server manually every time. By the end of this video, you'll have 3 practical skills. First, you'll understand how Azure VM Image Builder creates a repeatable custom image from a marketplace image or an existing approved source. Second, you'll learn how Azure Compute Gallery organizes images into definitions and immutable versions, then replicates those versions to the regions where they are needed. Once regional replication finishes, deployment teams can create VMs from a local regional replica instead of manually copying VHD files. Third, you'll understand the difference between generalized and specialized images. You'll know when Azure should generate a new host name, administrator configuration, and machine identity, and when a workload intentionally needs to preserve the exact state of the source machine. Manual post-deployment configuration is a slow-motion disaster. One team applies a security patch. Another team, deploying the same app days later, skips it. That's drift, a common trigger for cloud security incidents, with misconfigurations among the top culprits. A custom image with pre-baked settings, patches, and baselines kills that inconsistency at the source. Your deployment becomes a known good artifact every single time, not a prayer. Azure Compute Gallery, formerly called Shared Image Gallery, is not simply a storage account containing VHD files. It is a managed image distribution and lifecycle platform organized into 3 main levels. At the top is the gallery. The gallery is the container used to organize image definitions and control access. Inside the gallery are image definitions. An image definition describes a family of images. It includes properties such as publisher, author, SKU, operating system type, operating system state, processor architecture, Hyper-V generation, and supported security features. Inside each definition are image versions. The version is the actual deployable image artifact. Versions use a three-part number such as 1.0.0, 1.0.1, or 2.0.0. For example, a gallery named Production Images might contain an image definition named App Server Ubuntu. Version 1.0.0 could contain the initial approved configuration, while version 1.0.1 contains the next tested patch release. The image definition describes the product. The image version contains a particular release of that product. Let's lock in the Azure Compute Gallery structure. What are its three main levels? The answer is Gallery, Image Definition, and Image Version. The gallery organizes and shares the resources. The image definition describes the type of image, including properties such as operating system, OS state, architecture, Hyper-V generation, and security capabilities. The image version is the actual deployable artifact. We'll explain the OS state property next, because it controls whether the image is generalized or specialized. Time for a quick checkpoint. We saw that manual configuration across regions leads to inconsistent VMs, different patches, different settings. Compute Gallery gives us a single source of truth for our images. A generalized image is normally the preferred choice when you need to create multiple independent VMs. Before capture, machine-specific state is removed from the source operating system. Windows uses sysprep. Linux uses the supported deprovisioning process for the selected distribution and Azure agent configuration. When a new VM is deployed from a generalized image, Azure can provide a new computer name, administrator configuration, and operating system provisioning information through the VM's OS profile. Because each machine receives its own identity, generalized images are suitable for scale sets, repeatable server deployments, and automated domain join workflows. Notice the wording, suitable for automated domain join. Generalizing an image does not join the new VM to a domain by itself. You still need a domain join extension, configuration management tool, deployment script, or another supported joining process. A specialized image preserves the source machine's operating system state. That can include its hostname, local users, installed applications, and other machine-specific configuration. Specialized images do not use the standard OS profile provisioning process in the same way generalized images do. Use them deliberately for workloads that cannot survive generalization or for controlled lab environments that require an exact machine state. Time for a quick checkpoint. First, a throwback to Part 1. What's the major risk if you don't track test resources? And second, a new one. If you need every VM to join a domain with a unique name, do you generalize or specialize? The traditional image workflow starts with a marketplace VM. An administrator deploys the VM, connects to it, installs applications, applies updates, configures security tools, and adjusts the operating system by hand. For a generalized image, the administrator then runs sysprep on Windows or the supported Linux deprovisioning process. The VM is captured as a managed image or exported to a VHD. A managed image can deploy multiple VMs within its region, but it lacks the complete versioning, sharing, replication, and regional replica management features available through Azure Compute Gallery. If the image is needed in multiple regions, the administrator must create and maintain additional copies or use another distribution process. This works for a small proof of concept, but it becomes difficult to govern at enterprise scale. Every manual step introduces another opportunity for configuration drift, missing patches, undocumented changes, and inconsistent regional copies. The manual workflow has 4 major stages. Step 1. Deploy a base virtual machine. Step 2. Connect to it and manually install applications, agents, updates, and configuration settings. Step 3. Prepare the operating system for capture. For a generalized image, that means completing the supported Windows or Linux generalization process. Step 4. Capture the VM as a managed image or export its disks for another distribution process. The result may be usable, but the process is difficult to reproduce consistently. There is no source-controlled image template explaining every change. Versioning is often handled through names or spreadsheets. Regional distribution may require additional copying, and security teams may not know exactly what changed between builds. Azure VM Image Builder replaces that manual procedure with a declarative and repeatable image building pipeline. It's Wednesday afternoon, and Alex has just finished building another golden image by hand. He installed every update, agent, application, and security baseline manually. The work took 4 hours, and the next patch cycle will require repeating most of it. Azure VM Image Builder provides a better model. Image Builder is a managed Azure service built on HashiCorp Packer. You define an image template that identifies the source image, customization steps, validation tests, and distribution destinations. The source can be a supported Azure Marketplace image or an existing custom image. The customization section can install packages, copy files, restart Windows, run PowerShell, or execute shell scripts. The validation section can confirm that required services, applications, or configuration settings are actually present before the artifact is distributed. The distribution section sends the successful result to Azure Compute Gallery, a managed image or a VHD destination. There is no separate charge for the Image Builder service itself, but you still pay for the compute, disks, storage, networking, gallery replicas, logging, and other supporting Azure resources used during and after the build. Here is the Image Builder pipeline from beginning to end. First, you deploy an image template using JSON, Bicep, Azure CLI, PowerShell, or another supported infrastructure as code process. The template references a user-assigned managed identity. That identity receives only the permissions required to read the source, access customization files, use the selected virtual network, and write the finished image to its destination. When the build begins, Image Builder creates a temporary build environment and starts a VM from the selected source image. Next, the customization steps execute. These steps can install software, update packages, apply security baselines, configure monitoring agents, copy files, and restart the operating system when necessary. After customization, validation steps should confirm that the image is healthy. For example, validation can check that a required service is running, a file exists, an application responds correctly, or a security agent was installed. For generalized output, the final build process prepares and generalizes the operating system. Your customization scripts must leave the machine in a state where that process can complete successfully. Finally, Image Builder distributes the approved result to the configured destination. The service normally manages its temporary build resources, but failed or interrupted builds should still be checked for staging resources, logs, and diagnostic information. An Image Builder template contains several important sections. The source section identifies the starting image. For example, it might reference an Ubuntu Marketplace image or an approved image version already stored in Azure Compute Gallery. The identity section associates a user-assigned managed identity with the template. The virtual machine profile controls the temporary build VM, including its size and optional network configuration. The Customize section contains the commands that change the image. A Linux template might update packages, install nginx, add monitoring software, and apply a hardening script. The Validate section confirms that those changes succeeded. For example, it might verify that nginx is installed and that the service starts correctly. The Distribute section defines where the completed image will go. For Azure Compute Gallery, the distributor identifies the gallery image definition, output version, target regions, replica settings, artifact tags, and whether the candidate should be excluded from automatic selection as the latest version. Artifact tags can connect the image to a source commit, pipeline run, security scan, or change ticket. When the template is ready, deploy it and trigger its run action using the current supported Azure CLI, PowerShell, or REST interface. You just learned 2 ways to trigger an image builder build: the standard invoke action command and an alternative using AZ-REST. Running an image builder command from a laptop is useful for learning, but the real value appears when image creation becomes a controlled CI/CD process. A strong pipeline does not publish a production image after every code commit. Instead, a pull request first validates the image template, scripts, and infrastructure as code files. After approval, a controlled pipeline trigger creates a candidate image version. The pipeline starts the image builder run and monitors the last run status until the build succeeds or fails. When the build succeeds, the pipeline runs additional tests against a temporary VM created from the candidate image. Those tests might verify boot health, application availability, security agent status, listening ports, disk capacity, and vulnerability thresholds. The candidate version should initially be excluded from latest, so ordinary deployments do not adopt it before approval. After testing and change approval, the pipeline promotes that specific version for production use. Production templates still reference an explicit approved version rather than automatically accepting whichever version happens to be numerically highest. This gives you automation without sacrificing change control. What actually happens after you start the image builder run? Azure creates a temporary build environment and deploys a VM from the source image. The build VM executes each customization step in the order defined by the template. It might install an application, copy configuration files, apply security settings, restart Windows, update Linux packages, or connect to an internal configuration service. If the build uses a custom virtual network, the temporary VM can reach approved internal resources such as package repositories, file shares, configuration servers, or private endpoints. Validation steps then inspect the resulting machine. If a required service is missing or a test command fails, the build should fail rather than distribute a defective image. For generalized output, the final phase prepares the operating system for image capture. The finished artifact is then written to the chosen destination, such as an Azure Compute Gallery image version. Image Builder normally removes the temporary environment when the run completes. When a build fails, use its run status, staging resource logs, and customization logs to determine exactly where the failure occurred. Let's lock in 2 image builder concepts. First, what technology does Azure VM Image Builder use underneath its managed service? The answer is HashiCorp Packer. Second, where do you define the gallery destination, versioning behavior, artifact tags, and target replication regions? The answer is the distribute section of the image template. The distribute section controls the destination artifact. It does not guarantee how quickly every regional replica will finish. Your deployment pipeline should wait until Azure reports successful replication in every required target region before allowing regional production deployments. Here's the trap that even experienced admins fall into. You build a custom image, you set the image definition to generalized, but your VM wasn't actually generalized. The build itself may succeed silently, but the first time someone deploys a VM from that image, it fails to boot with a cryptic provisioning error. That's because the machine identity, the host name, the security identifier, was still baked in, and Azure can't provision a fresh identity. The fix? Always run sysprep on Windows. Or Wagant. Deprovision on Linux before capture. Or if you intentionally kept machine identity, mark your definition as specialized and own that trade-off. The mistake is the mismatch between the definition and the actual image state, not the choice itself. A specialized image can be the right choice when preserving the exact operating system state is an explicit requirement. One example is a legacy application that cannot survive sysprep or another generalization process. Another is a short-lived demonstration environment that must open in a precise pre-configured state. A third example is a controlled training lab in which each deployment must reproduce the same local configuration. But specialized images require careful sanitization. Before capture, remove production secrets, API tokens, cached cloud credentials, private certificates, personal data, deployment logs, temporary files, and any other information that should not appear in every clone. Review local user accounts and passwords. Do not distribute a specialized image with a shared weak credential. Also review domain membership, machine certificates, monitoring identities, cloud init state, and security agent registration. Cloning this state can create duplicate identities or broken management records. A specialized image is an exact state tool, not a shortcut around secure image preparation. Every Azure Compute Gallery image version uses a three-part version number such as 1.2.3. The first number is typically the major version. The second is the minor version. The third is the patch version. When a deployment requests latest, Azure chooses the highest eligible version according to the gallery's version selection behavior. A version can be marked exclude from latest. This is useful when you publish a candidate version, but do not want automatic deployments to select it yet. For example, version 2.1.0 can be published, replicated, and tested while remaining excluded from latest. But production systems should normally reference an explicit approved version, such as 2.0.5. Pinning production to an exact version gives you reproducibility. You know which artifact created each VM, scale set instance, or deployment environment. It also makes rollback, incident investigation, disaster recovery, and audit evidence much easier. Use latest only when automatically adopting the newest eligible version is a deliberate, tested, and governed policy. Azure Compute Gallery can replicate an image version to multiple target regions. Replication can occur across regions without requiring you to manually copy VHD files between storage accounts. However, replication is not instantaneous. The total time depends on the size of the image, number, and distance of target regions, replica count, replication mode, storage configuration, and current Azure service conditions. A small image with a few targets may complete relatively quickly. A large image replicated broadly may take much longer. Do not promise that every global image will be ready in a few minutes. Instead, monitor the image version's regional replication status. Only permit deployments in a target region after Azure reports that the version has successfully replicated there. This is especially important in automated pipelines. The image build job may finish before every regional copy is ready for production use. When you publish an image version, several replication settings affect availability, scalability, and cost. First are the target regions. Choose only the regions where the image is actually needed. Every additional regional replica consumes storage and creates another artifact that must complete replication before regional use. Second is replica count. Replica count controls how many copies of the image version Azure maintains for deployment operations in a region. A higher replica count can support greater concurrency when many VMs or scale set instances are created at the same time. It does not improve the runtime performance of VMs after they are deployed. Start with a reasonable count, observe deployment demand, and increase it only where concurrency requires it. Third is storage configuration. Supported replication storage options can vary by region and scenario. Standard locally redundant storage is common, while zone-redundant options may be available in supported locations. Fourth is replication mode. Full replication is appropriate for production images. Shallow replication can reduce publishing time for supported testing scenarios, but has limitations and should not automatically be used for production. Every replica has a cost, so match regional coverage and replica count to actual deployment requirements. Time for a checkpoint. Question 1. You set the image definition to generalized, but your VM fails to boot with OS provisioning timed out. What's the most likely mistake? And question 2. Why would you increase the replica count per region when replicating an image version? Think for a moment, then the answer appears. Azure Compute Gallery supports several sharing models. For internal sharing within the same Microsoft Entra tenant, role-based access control is often the simplest approach. Open the gallery, image definition, or image version and go to Access Control. Assign the reader role to the user, group, managed identity, or service principal that needs to read and deploy the image. The deploying identity also needs permission to create the destination resources, such as the VM, network interface, disks, and related infrastructure in the target subscription. Read permission on the image does not automatically grant permission to deploy resources elsewhere. Another important detail is discoverability. An identity using an RBAC shared gallery may not always be able to browse and list every shared image through the portal or command line. Provide the consumer with the complete resource ID of the approved image definition or version. For broader organizational or external distribution, review direct shared galleries and community galleries. Those models have different audiences, limitations, and governance implications. Use RBAC for controlled internal access and assign permissions at the narrowest practical scope. Time for a checkpoint. First, a throwback to Part 2. When you attach a high-performance disk to a VM, what's the factor that limits its real-world speed? And second, a new one. You've published image version 2.0.5 and 2.1.0. Your team specifies latest. Which version do they pull? Versioning is not only about assigning numbers. Each image version also needs lifecycle information. You can assign an end-of-life date to an image version. That date is informational. It does not automatically prevent someone from deploying the version after the date passes. Your deployment policy and automation must enforce the organization's retirement rules. You can also exclude a candidate version from latest while it is being tested. At the image definition level, document characteristics such as recommended minimum and maximum CPU and memory values, operating system state, architecture, Hyper-V generation, and supported security type. Maintain richer release notes in the same source repository that contains the image template and customization scripts. Those notes should identify operating system build, installed application versions, security baseline version, patch date, known limitations, pipeline run, source commit, test results, change approval, intended retirement date. Treat every image version like a software release artifact. Every image version and regional replica consumes storage. Keeping every historical build forever can create unnecessary cost and make the gallery difficult to manage. But deleting the previous image immediately after publishing a new one is also dangerous. A new image can contain a broken driver, missing application, failed monitoring agent, incompatible extension, security regression, or boot problem that testing did not detect. Create an image retention policy. For example, retain the current approved production version, the previous approved production version, one emergency rollback version, versions still referenced by active VMs or scale sets, versions required for audit or regulatory evidence. Only remove a version after the replacement has completed its observation period and no required deployment depends on the old artifact. Azure Compute Gallery versions are managed gallery resources. You cannot simply move an old gallery version into Azure Blob Archive tier. An exported VHD stored as a blob follows a different storage architecture and may have separate lifecycle options, but that is not the same thing as archiving a gallery image version. Before Image Builder can distribute a version into Azure Compute Gallery, the gallery needs a compatible image definition. When you create the definition, specify the gallery name, definition name, publisher, offer, SKU, operating system type, and operating system state. The OS state must match the actual artifact. Use generalized only when the source image has been properly prepared and generalized. Use specialized only when the captured artifact intentionally preserves machine-specific operating system state. That property is defined at the image definition level. If you need both a generalized and specialized form of the same operating system, create two separate image definitions. Also verify architecture, Hyper-V generation, and security type. A Generation 2 trusted launch source should not be placed into an incompatible definition. After creation, use the Azure CLI or PowerShell show command to inspect the definition and confirm that OS state, architecture, Hyper-V generation, and security capabilities match your design before building the first version. Now let's look at the complete Image Builder template as a production pipeline. The source section references an approved marketplace image or compute gallery version. The identity section attaches a user-assigned managed identity with narrowly scoped permissions. The VM profile defines the temporary build VM and, when required, the custom virtual network and subnet. The Customize section installs NGINX, security agents, monitoring tools, and organization-specific configuration. The Validate section confirms that the required packages are installed, the NGINX service is running, no prohibited service is listening, and the security agent reports a healthy state. The Distribute section publishes a new immutable image version to Azure Compute Gallery. It defines the gallery image ID, output name, target regions, replica configuration, artifact tags, and whether the candidate is excluded from latest. Artifact tags connect the image to the exact source commit, pipeline run, patch release, and change record. The version itself should also be unique. Never replace the content behind an existing production version number with a different build. Publish a new version so the deployment history remains traceable. Azure provides several ways to trigger an image builder run. The dedicated Azure CLI command group includes AZ Image Builder operations for managing templates, identities, outputs, and runs. You can also invoke the underlying resource action through PowerShell, a generic Azure resource command, or the Azure REST API. For a demonstration, a direct CLI run is fine. For a production pipeline, use a submit and monitor pattern. First, submit the build request. Second, capture the template resource and pipeline identifiers. Third, poll the image builder last run status rather than assuming that command submission means image creation succeeded. Fourth, fail the pipeline if customization, validation, generalization, or distribution fails. Fifth, inspect the output artifact and wait for successful replication in every required region. The exact command and API version can evolve, so validate the example against the current Azure CLI and Image Builder documentation before recording or placing it into a production pipeline. Let's lock in the command line workflow. Which Azure CLI command group is designed specifically for VM Image Builder? The answer is Azure Image Builder. What should your pipeline monitor after starting the run? The answer is the Image Builder last run status, followed by the output image version and its regional replication status. A successfully submitted command does not prove that customization, validation, image creation, or regional replication succeeded. Automation must verify every stage. Now let's connect versioning to production safety. You publish version 2.1.0 and mark it exclude from latest while testing. Which version should your production deployment use? It should continue referencing the explicitly approved version, such as 2.0.5. After version 2.1.0 passes image validation, security testing, application testing, replication checks, and change approval, production can be deliberately updated to reference 2.1.0. Why not simply use latest? Because explicit version pinning makes deployments repeatable and gives you controlled promotion and rollback. Here is the complete production pipeline. An engineer updates an image template, customization script, or package version in source control. A pull request validates the code and requires review. After approval, the build pipeline creates a unique candidate version and starts Azure VM Image Builder. Image Builder deploys a temporary build VM, applies the customization steps, and runs the defined validation tests. If validation fails, the pipeline stops and no production image is promoted. If validation succeeds, Image Builder publishes the candidate version to Azure Compute Gallery and replicates it to the selected target regions. The candidate remains excluded from latest, while additional tests run against VMs deployed from that exact version. The pipeline verifies application health, security agents, vulnerabilities, boot behavior, and regional replication. After approval, the organization promotes the specific version. Production infrastructure as code is updated from the old approved version to the new approved version. The rollout begins with a pilot group, continues through controlled deployment rings, and preserves the previous version for rollback. No manual VHD copying. No mystery configurations. No untested version silently becoming production. Here are the 3 most important lessons. First, use Azure VM Image Builder to create repeatable, source-controlled image builds instead of configuring every VM manually. Include customization, validation, managed identity, networking, logging, and error handling in the design. Second, use Azure Compute Gallery to organize images into definitions and immutable versions. Then replicate approved versions to the regions where they are required. Monitor replication rather than assuming that every regional copy is immediately ready. Third, treat image versions like software releases. Publish candidates as unique versions, exclude them from latest while testing. Promote them deliberately. Pin production to explicit approved versions, and retain known good rollback images. That is the difference between merely capturing virtual machines and operating an enterprise image management platform. Once your custom images are built, tested, versioned, and replicated, the next step is to deploy them consistently through infrastructure as code. Bicep, Terraform, ARM templates, and deployment pipelines can reference an explicitly approved Compute Gallery image version. That allows the same reviewed artifact to be used for individual VMs, virtual machine scale sets, Azure Virtual Desktop Session hosts, and standardized application environments. Before moving to the next lesson, complete one practical exercise. Create an Azure Compute Gallery. Add one generalized image definition. Choose the correct operating system state, architecture, Hyper-V generation, and security type. Then sketch an image pipeline containing 5 stages: build, validate, publish, test, and promote. That exercise will teach you more than manually capturing another one-off VM. If this series is moving your career forward, hit like, subscribe, and the bell. Every video adds a real marketable skill you can put on your resume tomorrow. Now go build a gallery, version an image, and never copy a VHD manually again. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.